Hello and welcome to this tutorial on Flexcom Wind. My name is Angus Connolly and I am the product manager for Flexcom software. In this tutorial I am going to show you how you can construct and perform a time domain simulation of a floating offshore wind turbine using Flexcom Wind. Flexcom Wind is a dedicated module in Flexcom which is tailored specifically towards the modelling of floating offshore wind turbines. So let me introduce you to the package first and walk you through the various inputs screens. At the moment we're looking at the animation module, or the model view, which actually shows you the structural response as a function of time. But now let me switch over towards the actual model building aspects. So this is the standard Flexcom interface, which you're no doubt familiar with at this stage. It's got the keyword file and so on. In the middle here there's the input deck. What I'd like to do now is to invoke the Flexcom Wind module, so I'm going to go to Tools, Model Building, Flexcom Wind, and this launches a separate module which I've just opened up here in the background. So the main purpose of Flexcom Wind really is to facilitate the development or the creation of such models with relative ease from a user perspective. So if you didn't have any previous experience with Flexcom, or indeed if you're an experienced Flexcom user, Flexcom Wind makes it very easy to construct a model of an offshore floating wind turbine. So the package itself, it resembles Flexcom in some respects in that the model view is obviously common, so that this looks exactly the same as the Flexcom model view. But in terms of how the data is inputted, it's not defined in terms of keywords as you'd normally have with Flexcom. It's highly modular and it's component based. So let's look at that component architecture in a little bit more detail. So at the moment we just have one sample model in Flexcom Wind. We hope to add others over time. At the moment it's just this OC4 semi-submersible floating platform. There are two windows here on the left hand side. One is called Structure and one is called Simulations. The Structure view is basically the physical geometry and the makeup of the structure itself. The Simulations then is analogous to the load case section in Flexcom, where you define wind and wave loading and solution parameters and so on. So let me just open up some of these components. The first component I'd like to show you is the blade component. So each of these blades on the turbine are defined in terms of a detailed geometry. So there's a local span would be the distance from the root to the tip along the blade. There are various curvatures and offsets, and also more importantly an aerofoil, which is a shape at that particular location. So you can see right at the root of the blades it uses a cylindrical profile, and then as you move further out it uses different aerofoil shapes. All of these aerofoils that you see on screen here come pre-packed with Flexcom Wind. They derive from INREL's FAST program. I guess I should maybe have stated from the outset, I suppose, in terms of the theory. Flexcom is obviously a structural analysis solver, but we've coupled Flexcom with an aerodynamic solver known as FAST, and when we run the Flexcom simulation it actually performs the aerodynamic computations via algorithms which come from this other third-party software called FAST. I'll go into that in a few moments in more detail. For now, let me just continue on with the model building process. So once you have the blades defined in detail, the next step is to define the tower, I guess. So the tower would be the mast, or the vertical portion, as we see here on screen. It's just defined in terms of simple geometry, how tall it is and so on. You also define some material properties such as Young's modulus and shear modulus. So that's basically the tower component, and we've already covered the blade component. If I just briefly look at the turbine component, this I suppose links the blades and tower together and specifies more inputs than you have already defined in some of the other components. So in terms of the blades, there's the pre-cone angle and the blade pitch. If you're not sure what any of these terms mean, you just press the F1 key and it brings up online help for the particular component that you're currently considering, as well as giving you a detailed description of what the inputs are. There may also be hyperlinks to further articles. So for example, you can look at the turbine geometry here, you can see what the blade pre-cone angle actually means, and shaft tilt and so on. So I'll switch back to the turbine component. You also define a number of properties in relation to the rotor in terms of spin speed, shaft tilt angle, overhang, and inertia, and so on. Then a cell, which houses like the gearbox and the workings of the turbine in terms of its mass, where it's centered. You also define, in terms of the control systems, Flexcom, as well as interacting with FAST from an aerodynamic perspective, which links up to FAST aerodynamic module, it also links up to FAST's servodyne module, which allows you to model the control system. So, for example, at very low wind speeds, the turbine is allowed to rotate freely. As the wind speed picks up, the gearbox resistance might be tuned up to provide greater resistance and maximize the power extraction. At very large wind speeds, blade pitch angle might be adjusted to feather the blades and to shed additional power above and beyond the rated power of the turbine. This will all be very, very familiar to anybody who's got any experience in modelling offshore wind turbines. So the inputs here in Flexcom are very, very similar to other packages, for example FAST itself, or indeed other simulation software packages in this space. That's the turbine. Let's move on to the floater. The floater really is the portion in yellow you see here. So it's a series of columns and cross braces and pontoons. You define that in terms of its geometry, in terms of the sizes of the different columns, pontoons and cross braces. Define the mass and buoyancy. So at the moment the mass of the structure is concentrated at the center of mass. The hydrostatic stiffness terms, which are used to simulate the resistance of the structure to slight changes in vertical displacement as it moves up and down with respect to the water. These are what are known as the hydrostatic stiffness terms. These terms would come from a hydrodynamic simulation of the structure, which you might do beforehand in WAMET, where you would solve potential flow theory using radiation diffraction techniques and come up with a series of matrices which characterize the responses of the structure, namely force REO coefficients, which define the high frequency excitation forces of an instant wave at a given direction and period. These are defined in an REO file. Also, you can have second order low frequency wave drift effects, which can be defined in terms of QTF, or quadratic transfer functions. So this, and also the added mass and radiation damping matrices. So where do all these come from? All these would come from a hydrodynamic solver such as WAMET or ANSYS Aqua. So these would be third-party hydrodynamic simulation tools which would take a structure and apply a series of wave excitations to it for, say, a particular frequency, a particular direction, and they use pressure integrals around the shape of the body to come up with forcing functions, namely force REOs. Without wishing to oversimplify, that's basically what they do. So what we've done is we've built a tool called the Hydrodynamic Data Importer, which you can launch from Flexcom itself. From here you can select from a selection of packages. There's just 3 there at the moment. We'd hope to expand that over time. Let's say we select ANSYS Aqua. You just specify the path to the output file from your hydrodynamic solver, and then a folder on your hard drive to accept the inputs in Flexcom format. Press the run button and it comes up with a series of files like added mass.incx, radiation damping.incx, etc. and you just populate these fields here with the names of those files, which contain the data which is transferred from a hydrodynamic solver like Aqua or WAMET into Flexcom's format. So the majority of the excitation on the floating body, it comes from these force REOs and also added mass and damping, which simulate the potential flow in terms of the wave excitation forces, the radiated forces, and diffraction forces, and so on. Coupled with that, you can also superimpose some viscous drag effects. So these are Morrison equation terms on the structure themselves, which give some degree of nonlinearity as well above and beyond what you get from potential flow theory. So you can do both options in Flexcom, and obviously you have to calibrate the effect of the viscous drag terms by comparing your Flexcom simulation numerically with either another software code or perhaps some tank tests and so on, just to get the selection of those coefficients in terms of viscous drag to get those calibrated. The final step in the model building process is to define the mooring lines, which I'll show you on screen here. Switch to an elevation view and zoom in. So these are just cables which link the floating platform to the seabed at the anchor points. So defined in terms of geometry, like length, mesh density, which defines how many finite elements are used in each line, hydrodynamic coefficients, and some structural properties like axial stiffness. That concludes the definition of the structure. So the structure is completely in place now and is ready for the simulation. What we need to do now is to go on and define some loading on the structure, which we do in the simulation component underneath. So there's a couple of other components here. The first one is the environment, which means it defines the properties of air and water depth and so on. We also define a seabed stiffness. We can actually define, in this case it's quite simple, it's just a simple flat frictionless seabed. We can simulate arbitrary seabed topographies with Flexcom as well, which might have an impact on the behavior of the mooring lines if it's touching an arbitrary seabed as opposed to just a very flat surface. So that's the environment. In terms of the loading, we have a couple of other components. Let's say we have one here for look at the regular wave loading, very simple irregular area wave. We could go on and define random sea loading in terms of John swap or other types of wave spectra. For this simulation, it's just a regular wave for simplicity. We also define the wind loading. So the wind loading is defined in terms of typically a wind speed and nominal wind speed and a shear exponent, which means that wind shear effects are taken into account. So the wind at the turbine, the tower, the tip of the tower it will be different to what it is at the water surface due to the wind shear. We can also define a time varying wind, like a time history of wind inflow, and in order to do that we use another module from this fast software called Inflow Wind, which allows us to specify arbitrary variations in wind velocity in time and space, so we can simulate full 3D turbulent wind inflow if we require. For this case we're looking at here, it's more of the wind is time varying, but we don't consider spatial variations, so it's a relatively simple input. Moving on to the solution parameters, just running this for about just over 1,000 seconds using a fixed time step. So when you run this simulation in Flexcom, I won't run it now just for efficiency, but when you run this in Flexcom Wind, what it actually does is it creates input files for the mainstream Flexcom product in the background, which I can show you here as well. So there's an option here to just open this as a Flexcom project. So users who are already familiar with Flexcom would be very familiar with all the types of keyword inputs that are in Flexcom. So we'll just wait for Flexcom to load. Here we go. So when you open this project in Flexcom itself, if we look at the model, there's a lot of different parameters defined at the top, and each of these parameters basically corresponds to one of the inputs which you've already typed into the Flexcom Wind module. So it's building up a static analysis, static equilibrium solution for this structure based on all of the inputs we've defined. So you can see that the blade and turbine and tower inputs and all that stuff there. And if we go down to the mainstream sort of standard Flexcom inputs, I'll just search for the line command just to give you an idea what happens. If we look at the tower, how that's modeled in Flexcom, it is just a series of just turn off these panels so you can see, switch this to black so you get a better view. So we're using a series of beam elements in Flexcom to model the tower. We're also using a series of beam elements to model the substructure, the floater, also the mooring lines, and all of these are defined here in using this lines command in Flexcom itself. If you're just wish to use Flexcom Wind, you may need to go into the mainstream Flexcom product itself and make some additional changes. For example, if you wanted to put in a different mooring configuration. This module Flexcom Wind at the moment is just kind of it's in its infancy, Flexcom Wind, the module itself, so it's hardwired just to handle a semi-sub platform with 3 mooring lines. So if you wanted to put in 6 mooring lines instead of 3, then what you'd go in here do is go into the Flexcom command line and start copying some of the lines there for the mooring lines and scroll down here. It's all neatly counted, so you can see what all the inputs means. It's got a line called mooring line. It's got a certain length. For the start and ends of the mooring line, it's got XYZ coordinates and space, and it's got some mesh density. So you could easily copy that block of lines and paste it in again and rename it to mooring line 1B for a copy of that line with some slightly different anchor points or connection points at the top. I won't go into any more detail in terms of Flexcom itself here, because there's quite a range of tutorial videos on Flexcom itself. Just to make you aware that if you are a user of Flexcom Wind, that this is what happens in the background. It actually runs a Flexcom simulation using very standard Flexcom inputs, which are derived from the inputs which you type into the Flexcom Wind box itself. So once the simulation, as I said, I won't bother running the simulation because it might just take a few moments to complete, but once the simulation has completed in Flexcom Wind, we'll switch back to here, it presents the results so you can view these results. This is the wind velocity at the top of the tower. So you might recall I mentioned we have a time varying wind time history, so it starts off at a low wind speed and gradually ramps up to higher wind speeds as a function of time. If I step onto these plots using the arrow keys there, I'm on the second plot now. This is the rotor speed. So you can see the rotor speed starts off quite slowly, ramps up to a certain level, and obviously it holds constant then as we hold the wind speed constant. And you can see the effects of transients between the regions of constant wind speed, where the control system is modifying the behavior of the turbine while the incident wind speed is varying, and eventually it reaches equilibrium. You see there are very small fluctuations in these plots, and these fluctuations correspond to the regular wave excitation. As the structure is heaving and pitching, we see slight changes in relative incident wind speed on the blades as the structure is responding to the wave action. We also would see some high frequency variations potentially as the blades spin around the axis as well. So that's the rotor speed, generator torque, again blade pitch as we've seen, which was controlled by the control system algorithm which we defined. And then the most important part really is the electrical generator power. So this is a 5 megawatt turbine, and you can see that for the lower wind speeds it doesn't, it has no power, little power. Then it reaches a power of about 3 megawatts at the intermediate wind speeds, and then for the higher wind speed sections it's got the maximum rated power of 5 megawatts. And just in the region of those two, there is some sort of time lag in terms of the response of the turbine matching or becoming in equilibrium with the incident wind conditions. As well as looking at the plots, you can also look at an animation from Flexcom's model view. It shows you the response of the structure as a function of time. So I guess you really need to start working with Flexcom Wind, or indeed the mainstream Flexcom version itself, to create offshore wind turbine models of your own to see how it pans out for you. If you need any further assistance, there is some useful help. Just go on to my help screen here. I'll just look at the online version. There's a dedicated section here on Flexcom Wind. It gives you information on all the various components, like say the turbine component. It speaks about all the various inputs, where they are, what they mean. There is also a theoretical section in wind turbine modeling, which goes into the underlying theory about how Flexcom couples to FAST. I might just mention this briefly as well. So Flexcom doesn't really know anything about aerodynamics. It's primarily a structural solver, so we've coupled it to another program called FAST, which is an industry recognized tool for simulating aerodynamic forces on such structures. At each solution iteration, Flexcom evaluates the hydrodynamic and structural loads. FAST evaluates the aerodynamic loads, and these are transferred from Flexcom to FAST as point forces at the hub node. And this transfer of data happens at every single solution iteration. So the the process continues until solution convergence is achieved, whereby Flexcom and fast inputs are taken at every iteration. So both solvers operate in tandem. So in terms of just some of the limitations of Flexcom Wind, because it's quite a new product, I may as well just mention one or two of the limitations. First of all, on the front end, on the user interface, the user interface of Flexcom Wind is just geared towards modeling a semi-sub platform. So if you wanted to model a spar type FWT or a TLP system, then you wouldn't be able to use Flexcom Wind at the moment, but you would be able to do that in the mainstream version of Flexcom by just modifying the keyword entries directly yourself. And as I said, there's tutorials and model building in Flexcom. If you haven't already watched those, I suggest you have a look at that as well. That's just in terms of the front end of the user interface. In terms of the theoretical, the finite element representation of the floating wind turbine, we have one or two limitations which we need to address also. Namely, the blades themselves in the Flexcom solution are assumed to be rigid, so we do not consider local blade deformations under the action of wind loading, which can in turn affect the aerodynamics on the spinning blades if the blades are themselves to deform. Also, the effects of the rotational inertia of the spinning blades is currently neglected in the Flexcom solution. So Flexcom Wind is very much a work in progress. We are continually developing the software, and in the next release of Flexcom, we will hope to address some of these limitations with the user interface and in terms of the finite element modeling as well. But for now, that concludes the tutorial on Flexcom Wind. I hope you've enjoyed it. But if you have any further questions, please don't hesitate to contact either myself or our technical support team, or indeed consult the online help as well, which is a very useful resource, and the standard examples provided with the software.